Hello, welcome to Electron Control. So in this video, I'm going to show you how to undertake least squares using MATLAB and Simulink. So rather than have an actual real system to generate input and output data from, initially on this video, I'm just going to use simulation to capture input and output data. So the system that we're using is a mass spring damper. So it has your mass, stiffness, and damping coefficients. And the application is a suspension system. So it's a white box model that we're using, and it's in the form of a discrete time arcs model. So we're going to estimate the physical model parameters M, K, and C. So in terms of the first point I said, so in terms of the real system, what you can see here is the actual system. So I'm using this transfer function here to effectively use this pulse generator, applying this to the actual system, and then getting a system response. And you can see here in terms of the system response, so you can see the measured, which is from our actual system, and then the simulated from our estimate. Okay, so and you'll understand this a little bit more when I go through it. So you'll see pulse generator. You'll see I've put a little bit of noise on the data as well. I'll talk a little bit more about that when we get into Simulink. And what you'll see is I'm effectively storing my known input values and also my output values. And here you can see time. So where I've got this clock and then I'm storing the time. And then this is using the least squares algorithm. This is the estimate I get for G of S. So that's the actual system, and then this is the estimate. So you'll see there's a little bit of error. But it's quite a close match. So if we're looking at the Simulink model, the first thing to point out is the simulation time. So I've set it for 1,000 seconds. So if I go to the pulse generator, you'll see that I've put an amplitude of 1, period of 500 seconds. So we expect to effectively get 2 periods, and the pulse width is going to be 50% of that, so effectively 250 seconds. If I go to the 2 workspace blocks, you'll notice that my sample time here is set as 1, and you see the variable name u, because obviously out.u, array, and then 3D array. And then again here it's the same, sample time y, so just make sure you're consistent on these in terms of the sample time. And then in terms of the band limited white noise, what I've done is I've just put a value of n in there, because then what we can do is specify it within the MATLAB script. So now if we're looking at the MATLAB script, we've got the usual commands here to clear anything previously, graphs, workspace, and command window. And then what you'll notice is the n that I told you previously for the noise power, you'll see I've specified a value here. And then I've got here sim, and then in brackets, and this is effectively the name of the Simulink file that we were just looking at. So if I run that section, you'll notice there I get my data out. So in terms of ants. So if I double click on there, sometimes it's not a bad thing to go to look into the data and then to look at the name of the file. So you can see in this case it's ants.time. Okay, and like for example tout's a time, ants.tout. Hence that's why when you plot in your graphs that you would use ants.tout. Right, then what we're going to do is we are just now going to rename the files, so t, u, and y. So we're going to take ants.time, ants.u, and ants.y, and then convert them into t, u, and y, and then just plot them then on a figure. So you can see here figure, so t against u, so these 2 data points here, and then t against y. So it's effectively time against input, time against output, and then the legend is just input, output, and then grid on, then usual line just to set the areas size 30. So if I run that now, there you can see you've got the data. So that's your pulse that you generated, and here is your system response. So this is the data that we're using to represent our real system in terms of the mass spring damper that we're using to simulate a suspension system. So quite a simple model, especially considering it's suspension system. It's quite a simplified model. And one thing to note is you'll just notice here these are, for the time being, they're just transposed. So that there just means transpose. So if then I move on to now doing the parameter estimation via least squares. So you'll notice here is the least squares equation. So theta hat equals inverse phi transpose multiplied by phi brackets times phi transpose times y. Okay, so what we need to capture obviously is phi and y, where phi is just the matrix that consists of past known and measured inputs and outputs, and y is effectively the outputs. Alright, so what we're going to do is we effectively populate this, so this phi and this y, based on the data that we've just captured from the real system, or in this case obviously the simulated system. So what we're first of all going to do here is go n is equal to length of u. So we're going to first of all just determine the length of u, which in this case, I'll just section it off, run that. There you'll see n is obviously 1001, and you'd expect that to be the case because you can see that these are just 1 times 1001. Right, and then in terms of y, what we're going to do is we're going to capture the data from this y vector, and we're going to take it from 3 to n. Okay, and that's always, that 3 there is always the case, that you'll always start from the third value. And if you look at the reason behind that is because because it takes you, if you think about it, it takes you the first 2 known measurements, input and output, to effectively form the first row of this of the observation matrix. So it's always 3 to n, and n in this case is 1001, and then phi then is just constructed based on all the values from, you can see here, minus y of in brackets 2 double dot n minus 1, and then you can see here n minus 2, n minus 3, and n minus 4 for inputs. And this will just effectively just construct based on all the past values for the outputs, starting from n minus 1, this one starting from n minus 2. And this one again for the inputs, so it'll be 2 to n minus 1 and 1 to n minus 2. Okay, so if we just section that off and then let's run that. So what you'll notice is your y is as you expect, 99 times 999 times 1. Okay, and then if we go to our phi here, it consists there of all the, in this case, the measured output, and here the known inputs. So obviously in the known inputs, you know that it's just going to go from 0 to 1. So you've just got effectively 2 cycles of just of a step input being applied and then removed. And then you'll see how if you look into a bit more detail and you simulate it yourself, you'll see exactly where these values come from. But you hopefully should be able to see from this where exactly they do come from. So then if I then run the whole section, so run simulation, you'll then see theta hat. So this is then effectively estimated the 4 coefficients. So if you remember in the vector where you had A1, A2, B0 and B1. So these are effectively your coefficients now, whereby you can construct your transfer function, whether that's g of z or g of z minus 1. Okay, so that is effectively your estimated model. And then what we can do here is we can construct the transfer function of the estimated model. So what we can do, we can go theta hat and then specify the values that correspond to those in there. So again, theta hat 1, 2. And if we look in there, so if we double click on here, obviously if we look in here, so theta hat and then 3 and 4. So it's effectively selecting these 2 values and these corresponding to your B0 and B1, so your 2 numerator coefficients, and then theta hat 1 and 2, so here these being A1 and A2, and these corresponding to your denominator coefficients. And obviously the leading coefficient here that I told you, the leading coefficient is always equal to 1. So that's always equal to 1, and then theta hat, the next 2 coefficients that you're going to put in here, will be obviously 1 and 2. which are, as I said, A1 and A2. And then this value here is just specifying the sample rate. Because what we're going to do now is we're going to take this discrete model, and then we're going to convert it back to the continuous domain. So system here, CS, is equal to discrete to continuous, system CSD, which is obviously this, so discrete to continuous. So if we run that, you'll see there now we've got the continuous model. So the continuous model that we had at the very beginning. So that's your estimated continuous model. What I'm going to do is just delete that because we don't need that. And then finally, if we're just looking at the simulation, because what we're going to do now is just simulate the model that we've just effectively estimated. So what we're going to do is run from k is equal to 3, okay? So we're going to run k values through this equation here, all the way up to n. So it's going to be 999 values. So y hat of k is equal to, you can effectively see the form of this equation. So this is your original arcs equation. So effectively the past sample, 2 samples ago, past sample for input. So output, output, input, and input. And you can see this is effectively your arcs model. And then what we're going to do is multiply it by, rather than to begin with, it would have just been A1, A2, B0, and B1. What we're now going to do is just multiply it by theta hat, so the estimated values. And this line of code here is just what you need. It effectively just populates it, values as 0. Don't need to worry too much about that. And then what you can see here finally is, what I'm doing is I'm plotting ty. So effectively my estimated, my original model. So my simulated, my captured data from the real system that obviously we use simulation to do, and then t, and then y hat. So that's effectively there is my estimated output. So if I run that, what you can see on the legend is measured and simulated. So measured is from the real system, and then simulated is from the estimated model. So if I run that section, you'll then see this graph. And if we zoom in a little bit, you'll see the model's pretty good. Okay, it's quite a close match. And what I said in the lecture was that if we were to introduce more noise, so let's put a load of noise on it. Let's just do that. You'll notice that the model fit now, so you can see there, isn't quite as good. Okay, and that would obviously follow, that pattern follows as you continue to increase the noise on the data. And to kind of counteract that, what you can do, you can see now it's pretty pathetic, the model that you're capturing. There's a big error there. It's not really capturing what's going on. But what you could do is to increase the amount of data that you're capturing from your initial simulation. Okay, and I'll let you explore that further. So I hope that's been useful for you to understand a little bit more in terms of least squares. Contact me please if you have any questions.